Hello and welcome to all my dear students. So once again I welcome you all on this amazing platform of Physics Wallah where we are studying in excellence batch. So far we have completed the chapter Principles of Inheritance and Variation. Today we are taking the last lecture of this chapter where we are going to study about the different types of chromosomal disorders and definitely very important that how to solve pedigree charts. Number of students, they are usually facing this trouble. They don't know how to solve pedigree charts. So basically I have number of questions today with the help of which I think you will be able to, at the end of the class, will be able to solve the questions also. Chalo. So beta, in my last class I have told you about Mendelian disorders where we have discussed about sickle cell anemia, then some sex-linked recessive disorders like hemophilia, color blindness. Apart from this, some autosomal recessive disorders like, as I said, sickle cell anemia, thalassemia, phenylketonuria, cystic fibrosis, and etc. But today we are going to see some more genetical disorders under the heading chromosomal disorders, where actually the number of chromosome changes. There is some alternation in the number and the structure of chromosome. As a result, there is some change in the genotype and phenotype of an organism. In our syllabus, we have three types of chromosomal disorders, mainly Klinefelter syndrome, Down syndrome, and Turner syndrome. So first, starting with Down's syndrome. This Down syndrome is one of the example of trisomy type of genomatic mutation under the heading aneuploidy. Right? Now what happens in Down syndrome, beta? In case of Down syndrome, the person who is suffering from Down syndrome, the reason is that there is one extra copy of chromosome in case of 21st chromosome. So in case of humans, when 21st pair of chromosome makes its extra copy, so this causes Down syndrome. Now what will happen? Not totally, beta. We are having 46 chromosome. Now due to trisomy in autosomes, the number of chromosome in case of person suffering from Down syndrome will become 46 plus 1, that is 47 chromosome. And such a person will be showing symptoms like mental retardation. Mental retardation is one of the most common symptoms which you see in patients suffering from Down syndrome. What is the main reason behind Down syndrome? The number of chromosome increases by 1. The organism is now having total 47 chromosome and it is showing trisomy of autosome. Which chromosome? For 21st chromosome actually makes its one extra copy. Now moving towards the second type of disorder, which is Turner's syndrome. Now Turner syndrome is beta monosomy. Again, it is a type of aneuploidy where it is basically an allosomic monosomy which is seen in case of females when one of the X chromosome out of the pair get lost. Such females, they become sterile. So what is Turner syndrome? Turner syndrome means when one of the X chromosome gets deleted. Chromosome gets deleted. As a result, total number of chromosome will become 46 minus 1, which is 45. And how will you represent? Pair of autosomes are perfect, but one of the X chromosome gets missing. So the representation will be AA plus XO. O shows that now the second homologous chromosome of X is missing, which is a type of monosomy. This disorder is known as Turner syndrome, and obviously the patient, the woman who is suffering from Turner syndrome, will be sterile, will not be able to produce its offspring. Correct? Now, next type of chromosomal disorder is Klinefelter syndrome, which is actually a trisomy in allosome. It is basically a trisomy of allosome in case of males. Now, normally, what is the karyotype of male? Normally, in normal condition, karyotype of male is 44 plus XY. But that male who is suffering from Klinefelter syndrome, so male with Klinefelter syndrome, they will show trisomy. Klinefelter syndrome, they will show trisomy of their sex chromosome, where their sex X chromosome will make its additional copy. So male suffering from Klinefelter syndrome will have two X chromosome. That means over here X chromosome is making its extra copy. Is making its extra copy, because of which the total number of chromosome from 46 changes to 47. Here in normal condition there are total proper 23 pair of chromosome, but in a male who is suffering from Klinefelter syndrome will show total chromosome 47. As I already told you, one of the X chromosome has made its extra copy. I hope you have understood this. Such a male who is suffering from Klinefelter syndrome will show more of female characters called gynecomastia, right? Will start showing gynecomastia. That means that male, first of all, will definitely become sterile, will develop some mammary glands, will develop some high-pitched voice. So all these other features which a male who is suffering from Klinefelter syndrome will start developing due to the extra X chromosome copy. Understood? So these are the three disorders which mainly you have to study under the heading chromosomal disorder. Now with this, the chapter comes to an end, but yes, you need to learn to solve pedigree. You should know how to solve pedigree. So the next heading is how to solve pedigree. Now before beta I make you solve pedigrees, I just have something extra to tell you. Pay attention. Now we know that there are Mendelian disorders which can be easily traced with the help of pedigree charts. Now which can these disorders, they can be of two type. Either they can be autosomal, yesterday class I told you, or they can be sex linked. Now in sex linked, the gene carrying the disease can be located on sex chromosome, which is X, or on Y chromosome. If I talk about basically beta for Y chromosome, then you know Y chromosomes are restricted to only males. That means any disorder related to the gene located on Y chromosome will only be observed in case of males. Only males will be suffering from this disorder, which will be due to the genes located on Y chromosome. Right? Understood? Chalo. Now we are going to talk about X chromosome sex linked, which can again be of two type. X linked dominant. That means when the gene will be present in dominant state, then it will be able to cause the disease, or X-linked recessive, that means when the gene will be present in its recessive state in X chromosome, then only it will be able to cause the disease. Similarly, autosomal disease, which are equally distributed in both male and female. As you know, distribution of autosome is same in both the sexes. Can be either autosomal recessive or can be either autosomal dominant. So these many are the disorders which you have to actually learn how to trace in a pedigree chart. Okay, so now beta, if I am talking about autosomal recessive disorder, in that case the diseased person, suppose one of the autosomal recessive disorder is sickle cell anemia, right? Yesterday only I taught you about it, kind of a transversion mutation that leads to sickle cell anemia. The shape of the RBC changes from biconcave to sickle shape. Okay, now what happens in this? A person who is suffering from sickle cell anemia, that means he or she is carrying the gene responsible for sickle cell anemia in its recessive state. Now, suppose I am representing autosomal disease by A gene, right? Correct? Now, a person who is having autosomal, now there are three types of genotype possible. Either homozygous dominant for a gene, or heterozygous dominant, or homozygous recessive. Now there are three combinations of a gene possible: homozygous dominant, homozygous recessive, or heterozygous dominant. For autosomal recessive to occur, the organism, the male or female, should have this genotype. When the gene responsible for autosomal recessive is present in its recessive state, then only disease is possible. Otherwise, in two above cases, person will be normal. Right? Can become the carrier but actually normal. For autosomal dominant, the thing will become absolutely reverse. Dominant means that disorder which will reflect when the gene is present in its dominant state. Maybe homozygous, maybe heterozygous. So for autosomal, these two genotype means diseased. But homozygous recessive genotype means normal condition. Right? Understood that how are we going to denote the disease when it is autosomal recessive or when it is autosomal dominant? Autosomal dominant disease, like for example, myotonic dystrophy. So patient suffering from myotonic dystrophy is because he or she is having the gene present in its dominant state. I am not suffering from myotonic dystrophy because the gene which is responsible for this disease in me is present in its recessive state. So I am normal. Understood? Coming to sex-linked. Now in sex-linked, there are two conditions: dominant and recessive. For Y-linked, things are very clear. In Y-linked, only males will be affected. So Y-linked disorder charts are very, very easy to understand. The chart in which only males are affected, none of the female is affected, that means that chart is for sex-linked Y disorder. Right? Okay. So now talking about X-linked recessive and X-linked dominant. How will you denote them? Talking first to X-linked recessive, again means when X-linked recessive, like for example hemophilia. Now hemophilia is a disorder which is X-linked recessive. That means the patient who is having the gene for hemophilia in its recessive state. Now male and female, obviously here the denotion will change, because you know males and females, they are heterogamete, they are carrying different chromosomes. Males are XY, females are XX. Now in females there are three conditions: normal female, right? So the female which is not having any of the gene or any of the allele of the gene responsible for hemophilia is considered as normal. Now, if one of the X chromosome is having the allele of the disease gene, then such females are considered as carrier. They themselves are normal but can carry the disease to the next generation. However, third genotype means diseased female. In males, beta, there are only two genotype possible, either normal male or diseased male. I have already told you in my yesterday's class that males, they cannot become carrier for any X-linked recessive disorder because males are hemizygous for X chromosome. Correct? Now, coming to X-linked dominant, beta. In X-linked dominant, both these conditions are diseased. Males में तो कोई फर्क नहीं पड़ेगा. Males तो will remain. Males genotype will remain the same for whether it is X-linked dominant or X-linked recessive because you know they are hemizygous. But for females, the last two genotype will be diseased, considered as diseased, and this will be considered as normal. Understood that how do you represent the various Mendelian disorders in the pedigree chart? So if you remember this chart, beta, then it will be very easy for you to solve the pedigree problems. So considering you have understood the chart, now we are going to solve some of the question. First question says that study the given pedigree chart and answer the following questions. First is you have to tell that whether the trait is autosomal recessive, yes or no. So chalo, let's check. Question is saying that you have to tell that whether this chart is autosomal recessive. Okay. So if this chart is autosomal recessive, that means जितने भी आपको colored दिख रहे हैं, as many offsprings you can see colored, they are having the genotype small a. Let me use some other color pen. So there are two offsprings. Now this is first generation. Okay, I think this color is also not visible. Black will be okay. This is first generation. This is second generation of the chart, and this is third generation. Clear? Itna samajh mein aa gaya to everyone. Now first generation, they are normal. In second generation, you can see two offsprings who are diseased. So their genotype is absolutely very clear. Homozygous recessive AA. In third also you see one offspring is affected. So its genotype is also very, very clear. Now, to ensure that whether this chart is homozygous recessive or not, you have to solve this pedigree. Now, in first condition, beta, you see in first generation, this is male, I mean this is father and this is mother. Now, here, both mother and father, they are normal. They can be the carrier, but they themselves, they are not carrying the gene. So suppose both are heterozygous for the trait. Suppose that not two genotypes are possible, that is either homozygous dominant or heterozygous dominant. So if I consider that both my parents are heterozygous dominant for the trait, that means the possibility of their offspring having disease will be only 25%. That means every pregnancy can give the probability that 75% will be normal offspring and 25% will be diseased offspring. 25% is the probability. So that means when actually they produced how many kids? One kid. So first generation, one kid, second kid, third kid, fourth kid, fifth kid. So that means first generation parents, they got conceived 5 times and they are having 5 offsprings, out of which 2 of their offsprings are having the disease and remaining 3 are normal. Normal means they are actually, some can be like this or they can be like this. They can be either heterozygous or they can be homozygous dominant. But the ones which are diseased, they are absolutely having homozygous recessive genotype. So kya first and second is clear? Possibility you have checked. Now talking about the third generation, you see beta, the third child which is female, she got married to a male who is also normal. So female is also normal and male is also normal. This is the condition of first generation. Now in second generation, the normal female who can be heterozygous for the disease, as well as the male itself normal but maybe heterozygous, can marry each other. Again the same probability. That means 25% are expected to have the disease, whereas 75% chances are there that in each mating normal offspring can be produced. So these two people, they mated 3 times, they produced 3 offspring, out of which only 1 offspring is having disease, remaining 2 are normal, maybe homozygous dominant or heterozygous dominant. Like this you can see we have solved this chart for autosomal recessive. Considering that this is autosomal recessive, we started solving the chart, and at the end you can see all the genotypes are clear. We have cleared all the genotypes of every offspring and every individual shown in the chart, and finally you can solve everything. Nowhere you got stuck. So yes, this is true. It is autosomal recessive. True. Second, give the genotype of the member 3 and 4. So this is the member 3 and this is the member 4. So fourth member genotype will be homozygous recessive, right? So fourth member will be homozygous recessive, whereas third member will be heterozygous recessive. The third member will be heterozygous dominant, and fourth member will be homozygous recessive. Understood both the questions? If yes, then let's proceed further to the next question. Now what does this next question says? In the pedigree given below, indicate whether the shaded symbols indicate dominant or recessive allele. Also give genotype of the whole pedigree. Simply you have to solve this whole pedigree, but this time you are not having the hint. In our first question, beta, we had the hint that whether it is homozygous, whether it is autosomal dominant or recessive. You had the beginning. You had the beginning that okay, we have to solve the chart for autosomal recessive. If it is true, then true. If suppose answer would have been false, then you would have solved for autosomal dominant, then you must have solved for X-linked recessive or something like that. But there you had the beginning. Here you don't have the beginning, you have to assume it by your own self. In this pedigree, you have to assume by your own self. Chalo, check it out how to do it. Okay, now again 3 generations are given. In first generation you can see one male, that is father is diseased but mother is normal. In second generation you can see all the offsprings are diseased. They are having 4 children. 1, 2, 3, 4. All are diseased. Now in second generation, the diseased female marries a man, producing offsprings mixture. Same thing you can see in first offspring as well. Chalo. So I'll start solving this pedigree again, considering that this chart is also autosomal recessive. I may be wrong. It's just a hit and trial method. I may be proved wrong at the end, but it's just a hit and trial. So again I'll start question solving for autosomal recessive. Okay. Suppose beta this chart is for autosomal recessive. That means all the diseased offspring. Genotype is absolutely clear. Right? Yes or no? The offsprings whose genotype, who are colored. That means if I am considering this chart to be autosomal recessive, their genotype is absolutely clear, which is small a, small a. Now you have to solve and you have to calculate the genotype of the remaining uncolored organisms in first generation. Check this. Male is homozygous recessive. Suppose this female is, now this female either has to be homozygous dominant or heterozygous dominant. Suppose she is heterozygous dominant and marries a man who is homozygous recessive. So what is the expectation? 50-50% chances. 50% chance is of normal offspring, and in every pregnancy 50% is the chance to have diseased offspring. Correct? So when they mated first time, suppose see, normal. So when they mated first time, diseased offspring. When they mated again second time, diseased. Third time, diseased. Fourth time, diseased. So by chance, what happened in their every pregnancy, this 50% probability came more. This 50% probability came more, and by chance all the offspring got diseased, not a issue. Now, what happened next? Now, the first offspring married a normal man. So this is about first generation. Second generation में क्या हुआ बेटा? The diseased female marries a normal man. Suppose that normal man is also heterozygous dominant. In that case, again the same thing beta. 50% can be normal kids. 50% can be diseased kids. So that means, again you can check it out. Highly proved. 50% diseased, 50% normal. That means the genotype of the man over here will be heterozygous dominant. Talking about this also, same. Again, suppose diseased female, she marries a heterozygous dominant man. So 50-50% probability. So maybe one offspring became diseased, two became normal. That means this chart can also be autosomal recessive. Hence, I have proved to you. Now, the shaded symbol in the, now this chart is for autosomal recessive. I hope now you can continue solving the rest of the question by your own. Okay. Now, moving towards the next question, let's see. In this question, it is saying, in the following pedigree chart, the mutant trait, mutant means beta diseased trait is shaded black. The gene responsible for the trait is, now in this you have to solve again the same thing, whether it is autosomal dominant, autosomal recessive, X-linked dominant or X-linked recessive. So again, like second question, you have to start solving the third question also, where you don't have any idea, you simply have a chart, you have to start as hit and trial. Correct? And yes, in hit and trial you can start with any category. Like I always start with autosomal recessive. So again I will consider that this chart is again autosomal recessive. I'll try to solve. Suppose if I am right, I'll get my answer in one shot. Suppose if I am wrong, so I have to calculate the chart again considering maybe autosomal dominant trait, maybe X-linked dominant trait, like that. Cool? Understood what you have to do? Okay. Fourth option though you can beta neglect. Why? Because it cannot be Y-linked. As you can see, females are also affected in the chart. So fourth option in the question is absolutely wrong. Now you have to choose between the first three. Now first option says dominant X-linked. Second says dominant and autosomal or dominant and X-linked. Third says recessive and X-linked. That means it has to be X-linked. Now you're not going to solve this chart for autosomal disorders. You have to check mainly for X-linked. right? See, mainly it is for X-linked only. But yes, in second option it is given autosomal dominant or dominant X-linked. Chalo, so let's start for autosomal recessive to nahi ho sakta. Why? Because in the option autosomal and recessive option is not given. So we are not going to check this chart for autosomal and recessive. That means we are going to start our chart considering that it is autosomal dominant. Now, if suppose this chart is autosomal dominant, that means the number of organisms whom you see undiseased, whom you see normal, their genotype is clear. Definitely they are non-diseased, so their genotype is absolutely clear. That is, they all are homozygous recessive. Now you have to check the genotype of the remaining 1, 2, 3, 4 organisms, and you have to ensure that do they carry the trait in their dominant state or in recessive state. Right. First, suppose in first generation beta you see that the male is normal but he marries a defected female who can be either heterozygous dominant for the trait or can be homozygous dominant for the trait. Considering that she is heterozygous dominant, now what is the probability? Again, 50% probability of gaining normal offspring and 50% of the probability gaining the diseased offspring. So check out. What will you write? Now, first mating normal, second mating problem, third mating normal, fourth mating problem. Right? Now, in second generation beta you check the normal offspring marries normal women. All their kids are normal. None of them is carrying the disease. That means correct. In last, the last offspring, the diseased female, when marries a normal male, what is the probability? Again the same thing beta. 50% normal. Every pregnancy, 50% of them can be diseased. So see, this is normal, this is diseased, and this is normal. That means this chart is absolutely true for autosomal dominant. So it can be autosomal and dominant. Now you have to check that whether, now see, second option cannot be the answer right now because in second option one more condition is given, dominant and X-linked. So now you have to prove, one thing you have proved, that yes, it is autosomal dominant. Now you have to prove that whether it is dominant X-linked or not. Now suppose if this chart is true for autosomal dominant but not true for X-linked dominant, then in case second cannot be the answer. Then you have to go and check for third, whether it is X-linked recessive or not. Understanding my point? Chalo. So right now I'll just remove everything whatever I have written. Now we are going to check this chart for X-linked dominant. Now you know how to represent the genotype. Or first we'll check. It is easy to check for X-linked recessive. Let's check the third option. Suppose this chart is for hemophilia. X-linked recessive means one of the disorder is hemophilia. So all the offsprings whom you see diseased, their genotype is clear. Female is suffering from hemophilia. Here male is suffering from hemophilia. Female is suffering from hemophilia. Female is suffering from hemophilia. Now, when a hemophilic woman marries a normal man, see, man is normal, then all their male children has to be diseased. Their all daughters will be carrier and all their male children has to be diseased. But can you see how many male children do they have? One male children, second male child. So you can see one of the male child is normal and one is only diseased. But this is not the condition. If in case of X-linked recessive disorders, if mother is affected, then all their sons has to be also affected. None of the sons can be normal. That means this chart is not true for X-linked recessive. Why? Because only one of the male is affected, but this male is normal, and it is not possible because the mother is completely affected. That means third option is wrong. First is also now first can be alone correct, but second is more correct because it is true for dominant autosomal as well as it is true for dominant X-linked. So the answer of the question will become 2. Clear? Understood everyone that how you have to solve the pedigree charts? If yes, then with this I would like to give you some questions for homework as usual. And yes, I would like to say thank you for joining me. And yes, trying to solve the pedigrees. See you in the next lecture. Bye bye everyone. Take care.